Today, I'm going to focus on laser-based visible light communications. Very impressive from the number of previous speakers, outstanding work on LED. But in KAUST or at KAUST, we very much developing laser-based lighting and for visible light communications. Again, my name is Boon. I do have a Chinese name, Huang Wenxiu. Thanks to the inventions of LED, now we have very efficient LED and also being used in a very wonderful applications in Li-Fi. At KAUST, we again very much focus on laser-based lighting and also its applications in high-speed visible light communications and Li-Fi. So what are advantages of laser lighting? If compare, well, this paper is from Changming Li, UC Santa Barbara. If you compare LED and laser making 60-watt incandescent equivalent light sources, LED needs multiple LEDs to get to 60 watts equivalent. But for laser, it potentially be able to use a single diode to get to the same lumen and same performance. Another advantage of laser diode is droop. LED, we always observe droop. Droop means that when you inject high current into a diode, instead of keeping the external quantum efficiency constant, it tends to drop in efficiency. And for laser, under high injection current, the EQE stay fairly constant. So if we use laser diode to as light sources, it's easy to control and essentially a small footprint as well. And that would hopefully increase the reliability. In terms of speed, LED, look at the LED rate equations. Speed is very much limited by dominated by carrier lifetime, which is in nanosecond. Therefore, as previous speaker mentions, many of those other than the micro LED, many of the standard LED always give a bandwidth of about, say, a few tens of megahertz, and phosphor always give lower bandwidth than the LED. As for laser can easily be driven to beyond gigabit bandwidth, and even with a phosphor integrated onto the light bulb, you still be able to get beyond gigahertz of bandwidth. Other key challenges, Harold just now mentions a couple of the key challenges, but those are quite similar. In our case, for laser-based lighting, the light quality is always the issue, which is the CRI, and how to control the CCT, always the issue. And the high-speed transmitter and receivers are always in demand because by using a standard prop laser, we can only push the bandwidth by so much. And receiver, not having said receiver, the APD, although will be able to go up to close to about gigahertz of bandwidth, but if you want to handle we're using a single PD, silicon-based PD, to handle multiple gigahertz up to a few tens of gigahertz, it might be quite challenging. And the other directions that we are looking at is the omnidirectional receiver. This work is a very early work from KAUST working on the laser-based Li-Fi and lighting. Let me maybe, if you can forgive me for a while, I'll close this and then go back to the laser pointer. In this particular case, we use a blue laser diode for 15 nanometers and then excite onto yellow phosphor. Very similar to the LED white light method. But in this case, we use a single crystal, so that because it's a very, very focused beam, so single crystal YAG phosphorus is required to generate reliable white color light. And then test the measure at the system level. In this case, we get a CRI of not too good because we have a lot of missing spectrum and CRI of about 60. And CCT is still very much bluish color because still a lot of high intensity of blue light escape from the laser. Although it's a diffuse light that we are using for our system. And for the bit rate, we use a very simple OOK on-off keying method to get to about 2 gigabit per second. So the next step is to increase or to improve the color rendering index. So instead of using a single yellow phosphor, in this case, we are integrating RGB phosphor in a phosphor plate followed by a diffuser. To excite the RGB phosphor, we use a violet color LD laser diode, which is 405 instead of a blue color, and then guide it into the APD for measurement. We improve it to about 80 and then successfully tune the color down to about 4000 Kelvin. Yet still being able to keep it to 1 gigabit per second of data rate. To further improve the speed and also the CRI, we introduce a green color for perovskite nanostructures into the lighting system. So in this case, we have a blue color laser for close to 450 excite onto the green phosphor, and then to further increase the CRI, we add on to a red color nitrate phosphor and get about 90 in CRI and tune the color down to about a bit warmer white of 3000 something Kelvin. And as for bandwidth, we still manage to keep to about 500 megahertz or so. And under OOK, we managed to get up to 2 gigabit per second link. We bring this technology to underwater. I believe we are the earlier group to get into underwater communications using narrow beam laser technique. Early 2015 or so, we reported work on 2.3 gigabit per second by using a blue color laser. Blue and green are used because those are two colors that giving us fairly low attenuations in water ambient. In also the same year, by using a higher order modulation scheme, 16 QAM OFDM, we managed to get it up to 4.8 gigabit per second in underwater. Then we focus on pushing the distance, and distance that's I think the first one to break the 10 meters link is reported by Chaoshen. He's going to give a talk tomorrow, and we managed to get 20 meters. And then from 2017 to 2018, we very much focused on what the previous speaker, Professor Shi, was mentioning, very much on the turbulence, the bubbles, and salinity, temperature gradient, and etc. So those are all some of the selected paper. We do have more paper on this topic than what I listed here. And also before 2018, we successfully transmit video in water channel, streaming the video in water channel. Then 2018 onwards, Xiaoping Sun now is in with our Martin's group and Harold's group, begin to look into the non-line of sight underwater comm by using violet color to UVA diodes. 2019, adopting technology that we developed in BLC, we begin to send signal from the water, go through the interface and pick up the signal using the photo detector in the air. And also early this year, we successfully introduced or reported the deployment of a internet in underwater. A selected work that is our pet project that we have been working is placing the transmitter in underwater and pick up the signal by using drone. This work is quite interesting because student and collaborator in board can dive into the pool and then play with drone. And in this case, we managed to get 44 megabit per second, and the water depth is about 2-point-something meter. And then in the air, we have our drone fly 3.5 meter above. Also, another very nice demonstrations of the sensor network that we decided to place for environmental monitoring is to make a base station that is essentially our transceiver, and then with the sensor node placed in the test pool for to monitor the environment. We couple up the functions that we put into the probe, include the temperature, salinity sensor, conductivity, and pH sensor. Of course, do have a camera for video streaming as well in this case. Let me switch gear a little bit to go into the high-speed laser that we're developing. The DFB laser that we focus on is in blue color and green color. A couple of other side applications other than the visible light communications. This laser can also find applications in the atomic clock, for example, particularly for cooling or trapping the strontium, which happen in the blue color for 61 nanometer or so. And of course, in underwater comm, that is required because by using blue color, a very high purity blue color and green color, it depends on whether it's deep oceans, pure water, or the green color, which is in the bit more turbid water. We then be able to use it for communication as well as explore the applications in LiDAR. Other objective will be trying to match the FB laser and make the wavelength so narrow that you fall onto the Fraunhofer line. That is a missing line under the bright sun, under the sun spectrum. So doing so, the objective is very much is hoping to reduce the background noise into the detector. The way, well, in gallium nitride, we all know that it's quite difficult to fabricate and processing of the gratings and making any small features onto gallium nitride is highly challenging. In our case, we start from a ferrite rod laser and then place the surface grating, very high order grating. In our case, although we lost a lot of energy, lost a lot of power by using a high order grating, but managed to at least being able to bright it by using focus iron beam to control the wavelength. We did so in the green color wavelength. This case, we managed to get about 513 something 0.85 nanometers DFB with fairly narrow line width of 31 picometer or so, and still managed to get about 14 milliwatts of power. And what you're seeing here essentially is a first DFB laser fabricated in green spectrum. Another one that we are working on, another color that we're working on is closer to 480 nanometers. Well, those are the so-called sky blue wavelength, and similar fabrication technique starting from a ferrite rod laser and then put down the grating from the side instead of have to embed it just like any other DFB laser fabricated in indium phosphate or gallium nitride based material system. We managed to get a line width of, again, about 35 picometer or so. It's not the, I think we can get better than this, but our OSA, optical spectrum analyzer, very much giving us those resolutions. The signal SMSR in this case is fairly good. So I think it's among the best ever reported, which is above 40 dB or so. And again, we managed to keep it to about 14 milliwatts with a decent slope efficiency. We measure this in the VRC system, and in 16 QAM, we managed to get 10.5 gigabit per second by using this laser. And of course, other than we also have some, although it's not reported here, we also try to work on, we also working on the tunable laser, and so hopefully be able to get to a fairly reliable tunable laser, as well as being able to get into different color for WDM. And one day, hopefully be able to get to DWDM as well, if multiple wavelength in a narrow line width laser can be fabricated. Another class of light sources that we are working on is called superluminescent diodes. We know about laser. We also know about the LED. LED is spontaneous emissions, and laser, we know that is stimulated emissions. But in between the two classes of device, we do have the amplified spontaneous emissions that will give us relatively broad spectrum and also partial coherent photons. But in this case, we can get rid of a lot of the speckle pattern that's being formed, unlike the laser that give a lot of speckle patterns. But having a performance that is in between laser and LED. The way that we're making our SLD, or superluminescent diode, is having because it's a single pass means that photon will not oscillate in the ferric rod cavity, but we keep one of the facets vertical, and the other facets we cut it by or tilt it to about 12 degrees or so to suppress any lasing oscillations, so that to be able to tap onto the amplified spontaneous emissions to get into the SLD. We are among the very first group to report the SLD and apply into the in gallium nitrides and apply it to lighting. In this case, well, back in 2016 or so, we reported a SLD that well, at blue color, and give us about 1.3 gigabit per second, again by using a very simple OOK method. And the power in this case is relatively low, less than about 100 milliwatt or so. In order to increase the power span, we have been using the tilted angle with one facet tilted, the other facet as a reflector, to ramp up the power to about 470 milliwatt or so. This actually is the record. I think I still believe that is still the record high SLD power ever fabricated, and integrate into the RGB phosphor to get into the lighting system. We also test up the sample by using the perovskite phosphor because it has very good response time, and managed to get above 1 gigabit per second, and with modulations bandwidth up to about a gigahertz or so. And by using high order modulation, OFDM, for example, believe that be able to get beyond this number. And of course, some of the measurement is done in Sunan's group in Fudan, and it's a collaborative effort. We also look into the high-speed photodetector, and for high-speed photodetector, we work on gallium nitride-based material and convert into the micro PD array. Why micro PD array? We need small-sized devices for high-speed applications, and also if be able to detect the high density from one of the pixel, we can then turn off the other pixel to drive them into the energy harvesting component. This is one of the motivations that we work on the micro PD array. In this case, we managed to get our 450 nanometers PD. That's actually peak at 450 to give us a 3.2 gigabit per second modulations. while we are way fond on working on the simple modulations using OOK, by using simple OOK on a photo detector that we make on a substrate that it calls semi-polar InGaN substrate. It's a collaborative work with UC Santa Barbara as well, Steve Dembar and Suji Nakamura. We managed to get above 1 gigabit per second by using this simple method. This is not direct relevant, but we have this huge interest in working on the high-speed solid line optical wireless communications. And when you look around the high-speed photodetector in UVC regime, it's quite difficult to find a very good high-speed photodetector. For most of the silicon APD, for example, the responsivity become extremely low, lower than say 0.1 amp per watt or so. So in our case, we add a light converting material against using cesium lead bromide based nanocrystal to have a very, very fast response, so that be able to convert light into the green color light. Doing so, we'll be able to increase the responsivity in UVC wavelength, and also being able to use a standard off-the-shelf APD for very high speed detections. The speed that we are getting here is 34 megabit per second. It's not limited by the technique or the photodetector, but it's very much, we cannot quite find a good UVC laser to do this job. And most of the UVC LED even that we can find from our collaborators and in the market is simply too low a power for us to do a very, very high speed measurement. To increase the, this is one of the work. We also have other work on the OME directional PD. In this case, we use something quite similar to what Facebook has been reporting, the scintillating fiber, and to enlarge the detections area and then guide some of those light into a small APD that plays, excuse me, plays somewhere here. So when any UV light or even blue color light striking violet color light strike onto the fiber, it will then be converted into different color and eventually being guided, guiding the beam into the small APD material. Doing so, we'll be able to have a very, very large detection surface. We currently is about to report one that is mimicking the using fiber bundle to mimic the compound eyes from fly. So that again will increase the field of view and the detections area for couple of applications. In this case, it's very much focused on underwater application. Doing this, we managed to get 250 megabit per second in underwater channel, and bandwidth that we get is close to about 100 megahertz or so, because after the light conversions, the speed of the light conversions in the scintillating dye is not very high speed, but it's a proof of concept that be able to get to a higher speed and enlarge with a bigger field of view. With this, I'll conclude. I'd like to thank some of my funding agents, collaborators, and we do have in-kingdom collaborators, very, very strong communications group. Slim Malini, for example, has been collaborating with him in underwater, and a lot of material we get it from Osman Barker, Omar and Donald Bradley. Then we get some material from UC Santa Barbara, and some of the measurement that we are doing is early measurement is with Lincoln Ru and Ku Haozong. Sunan is another collaborator, especially on the superluminescent diodes. All right, thank you.